I apologize. This is not a talk about wave turbulence. So I'm sorry. Okay, so I'll talk about the Euler equations. This is I'm going to go rather quickly to some very classical things. Three conservation laws: conservation of mass, conservation of momentum, and conservation of energy. You see the pressure here. Total energy is related to the pressure by this law that the energy is the potential energy plus the kinetic energy. And when we're talking about polytropic gases, it's sometimes more useful to not work with the total energy as an unknown, but to instead work with the specific entropy, which is denoted capital S. And this is the pressure law for a polytropic gas. You have the classical 1 over gamma rho to the gamma of isentropic gas dynamics, and the E to the S is the E to the specific entropy. So for this talk, I'll look at the system posed either in the whole space or in a periodic box. I just don't want to worry about boundaries. And the problem I would like to understand is what happens when you start with smooth initial data. For how long can you propagate smooth solutions? So the initial time at which the data is prescribed, I'm going to call it T sub in, to T initial. And you prescribe some smooth initial conditions. And very importantly, I don't want vacuum in my initial data, so that my density will be bounded from below. It's very simple by modern PDE techniques, but it took up until sometime in the middle of the 20th century to prove that the system is well posed. So if you start with HS data, here HS is the Sobolev space with S derivatives in L2. You have locally in time an HS solution. And by standard continuation arguments, you can find a maximal time of existence, which shall be denoted by T star throughout the talk. So the HS initial data can be propagated up to T star as an HS function. Up to that time, everything is nice and beautiful. And something bad happens at T star. And we know, due to papers of many people, maybe the culmination is the paper of Tom Sideris, that generically T star will be a finite number. Most initial data for compressible Euler will develop a singularity. And what happens at this first singularity is kind of still, I mean, we're basically now learning everything that can happen at this first singularity. Generically speaking, what will happen is that you will have, just like in the previous talk, you will have a cusp forming. And generically, this cusp will be that of a C1/3 function. Again, not a discontinuity, but a cusp. The discontinuity, which is commonly referred to as a shock, occurs after this cusp has formed. And this is why Frisch and Fournier have labored this first singularity pre-shock. I will use the American version, pre-shock. I'm sorry for that. So whenever I'm referring to a pre-shock, I'm referring to a gradient singularity at which the fields are still Hölder continuous. Okay? And this is what happens in this numerical simulation. You have a density profile of 2D Euler, not 3D Euler. So density and then two space dimensions, and Euler flows, and a singularity forms. Now, what has happened is that somewhere around there's a cusp forming with respect to this direction, which is corresponding in this picture to x1. But in terms of x2, so in this way, nothing bad has happened. Okay? So not only did this cusp form, this cusp is in a way a one-dimensional cusp foliated smoothly in the other directions. And then that's kind of not so hard to understand. The question is what happens afterwards. And in one space dimension, you know, because of old papers of Glim and Khrushchev and many other people have naturally worked with this BV setup. They define weak solutions, and we all know about 1D conservation laws. But in multi-D, you can't afford to do that. That setting is just not going to work, and that's a paper of Jeff Rausch from the 80s. So instead, you have to just use all the physics you have, and what you expect is that from this pre-shock, you will have a shock surface emerging, and by that I mean a codimension 1 surface in space-time across which the density and the velocity will actually experience jump discontinuities. Okay, not Hölder singularities, but actual jumps. So this surface will, of course, only occur after T star. And you can imagine that in principle, if you run Euler even with a shock for a very long time, you will have shock collision. Two shocks will collide later. And you kind of know the time at which that should happen. So in order to prevent that, because I cannot prove any math theorems about shock collisions, I will cap my time horizon at the final time, which is of the order of the times at which you will expect shock collisions. Okay? So my entire analysis will be locally compact in time. And so my analysis will start at T in and end at T fin, but the blow-up time will be in the middle. Okay? Besides the shock surface, which is a codimension 1 surface of spacetime, there are other interesting surfaces of singularities appearing in the Euler dynamics. Maybe you should ask yourself, what is this pre-shock that was there initially? So it turns out that this pre-shock, which is, again, the boundary at which you can flow Euler forward in time and you see a cusp, not a jump forming, is actually a codimension 2 surface of spacetime. And these are later first singularities. I will draw a picture to explain. Of course, you want the solution produce entropy. And in addition to the shock singularities, because this is a system with multiple wave speeds, the initial Hölder cusp will be carried by the slow acoustic and the fluid velocity into other types of singularities which are not jumps. These are weak characteristic singularities. One is called a weak contact and one a weak rarefaction. And so the goal is to prove that this happens. Okay? That's the goal.
You seem to be saying in the first bullet point that the shock follows instantaneously after the cusp. There is no time separation. Is that what you mean?
I will draw a picture. So basically, this is an equation with finite speed of propagation. If the shock forms here at the first time, around here it has not yet happened. And because it has finite speed of propagation, the evolution around this point will continue as a smooth evolution for a while. It doesn't know that the shock forms. But instantaneously near this point, a shock, an actual jump forms. But these times will also form a singularity. It's just going to happen later. And these times is what I'm referring to as this codimension 2 surface. It's when these other points also now develop a cusp by themselves, which are completely independent of the shock a priori. And this is a peculiarity of equations with finite speed of propagation.
But is the surface of pre-shocks anything known about it as a smooth surface? As the surface of pre-shocks, you're going to form shocks at various points, and there might be a surface of cusps.
In the absence of symmetries, the answer is no. Without symmetries, that's what this paper is about.
Is this similar what you just explained with the pre-shock? Is that what you would see in burgers?
No, because burgers is 1D.
You can make it 2D too, right? But it's the same thing, which is that you have a pre-shock, in fact.
If you look at multi-D burgers, you will have a similar phenomenon, except you're not going to have multiple wave speeds. So you're not going to have these things. So you're going to have some of these features, just not all of them. Yes?
For the surface of a codimensional 2 surface, at the beginning, is it smooth?
The surface
So
itself,
does this mean that at the beginning it is smooth and after some time it becomes singular?
none of these surfaces are rough. All of these surfaces are smooth. Across these surfaces, the fields themselves, density, velocity, and entropy, they develop singularities.
Yeah, but what is the first singularities occur after time t star?
Okay, so I was planning to do this later, but I guess it's time for the board now.
Thank you so much.
So I will do it in the center. Okay, you have initial data. and you flow it forward in time, you will develop a first singularity. At this time slice, this is the maximal time of existence, T star. You cannot define a unique HS solution past T star. The HS norm has blown up. What happens afterwards? Well, in 1D, here's what happens. In 1D, you have three wave speeds: slow acoustic wave speed, fast acoustic wave speed, and the fluid velocity along which entropy is propagated. Along the slow acoustic wave speed, from this pre-shock, you get a surface which acts like a Cauchy horizon. The Euler equation does not know how to go past this place. On the part which is to the right of the pre-shock, you will have another surface which consists of subsequent pre-shocks. So along this place, the fields are C1/3 smooth. So these are subsequent first blow-ups after the first blow-up. And they happen because the field here is perfectly smooth. So it keeps evolving up until some point in which it develops itself a shock. Along this Cauchy horizon, everybody is smooth. It's just that because of causality, if you draw the light cones, the Euler equation is simply unable to tell you what happens afterwards. This is the picture in 1D. In multi-D, you should take this picture and moving in and out of the board in a parabolic fashion. So this pre-shock, which was a single point in 1D, becomes a curve. Out of this curve, you don't emanate one line, but rather a surface of pre-shocks. And this Cauchy horizon is again going to emanate from here. And it's going to look like that. And this is what I'm referring to. This is codimension 2 in space-time. This is codimension 1 in space-time. And nowhere on this picture is the actual shock curve, because I'm talking about propagation of acoustic waves at this moment. The shock curve is where in this picture? Well, I will hopefully tell you a bit later. Does this answer the question? Pierre?
How about the weak discontinuities that you mentioned?
One is this Cauchy horizon. This is a weak discontinuity. And there's another one here, which in order to talk about it, I have to talk about the shock. And because I have not talked about the shock, I'm not able to talk about that yet. All right, so maybe if we could go back to the slides, please. So this is the density field at the end of the previous simulation. There's a cusp, which is 1/3 at this point. So now you take your favorite Euler scheme. This happens to be a Wino scheme. Run forward, and this is what's going to happen. There's a shock propagating across a growing oval here. And these are weak singularities in which you have kinks, no discontinuities. They happen to be C1, 1/2 kinks. Precisely C1, 1/2. No better, no worse. And the goal, and this is what we've been working on with many people over the past 6 years, is just to prove this picture. That's all. So again, the goal for this program is to start with smooth data without vacuum, and then precisely describe how this first singularity forms, what the first singularity looks like, and then proceed and describe the Euler solution afterwards and obtain a full propagation of singularities result. In light of the many convex integration results that exist in the literature, which say that from the Riemann data you cannot forward in time describe a unique solution of Euler, I will now require that you're going to have some kind of uniqueness, because we do see shock waves stably no matter how we simulate them. So they're there, okay? So in addition to constructing the solution and describing all these singular surfaces, I will require that you also prove uniqueness. So that's the program. This program is completed in 1D or other versions of 1D. So you can say 1D by saying multi-D with spherical symmetry. That's the same, it's 1D. Or you can say 2D with azimuthal symmetry. That's the same, it's 1D, okay?
Sorry, can I ask a naive question about that?
Yes.
Maybe I should know this, but if you do a linear stability analysis of a front in burgers that is not really 1D, do you know if you know, like this David Cheng, whatever they call it, these techniques to see whether you will develop instabilities? For example, if you do with KDV, you put it in a channel that has a width, the soliton is no longer stable. Does that something happens like that with burgers? This is probably common knowledge, but I don't know.
I don't know, because the whole point of this analysis is that we do not write anything in the Eulerian frame. So the question you're asking is in the Eulerian frame, and I do not know the answer. Okay, so there was this very famous physicist called Singe, who had a famous daughter called Kathleen, who used to be a professor at Quran for a long, long time. So the Irish physicist Singe discovered in the late 30s that if you have an irrotational compressible flow, then of course everything reduces to the equation for velocity potential. And then the Euler evolution is simply the wave equation, in which the metric is the acoustic metric associated to the solution. And I've just written for convenience all the components here of the acoustic metric. C, whenever you see C, it's not a constant, it's the speed of sound. Okay, so C is just square root of dp rho. So you have linear combinations of velocity tensors and sound speed. And then, of course, Singe, who was actually interested in geometric descriptions of relativity, he went further, and he basically drew this very direct dictionary between general relativity and fluid and gas dynamics. And essentially, the remarkable thing is that although the underlying fluid dynamics is Newtonian on a metric which is dx cubed, on a box, the perturbations in sound, they follow dynamics which are Lorentzian in a curved geometry. And sound propagation is really exactly like light propagation. It follows null geodesics, just of this different metric. And this was a well-known statement in the physics community. It was rediscovered by many people. Another famous physicist, Andrew, known for Andrew radiation, he also rediscovered this. Weiser rediscovered this, and many other people rediscovered this, including Christodoulou, who also rediscovered this. And then, because they were experts in quasi-linear wave equations, they said, okay, now we can go to town on Euler, because we know really well how to analyze quasi-linear wave equations. And from this perspective, inspired by general relativity, Christodoulou was able to essentially flow the smooth initial data up to this first singularity. You know, this time slice at which I said the HS norm stops, he managed to do that, and he proved that there was no singularity prior to that, and at that time, it was not an implosion, it was not vacuum formation, it was a gradient singularity, okay? At one point. Sorry, Christodoulou does not describe that it's 1 point. There exists at least 1 point. Then with, this was later extended because Christodoulou only worked in the irrotational setting and isentropic setting. And then with Tristan, who is here, and with Steve, we took a very different perspective, and we basically said, well, the singularity can't just be some kind of random generic singularity. It's probably self-similar, and that's what we proved. That the first singularity is asymptotically self-similar, and it's based on the backbone of a multidimensional Berger self-similar profile. So basically, these two pictures paint a pretty papers paint a pretty complete picture of what happens at the first time of the singularity. What happens afterwards? Afterwards, this is the shock development problem. And in the absence of symmetries, again, this is open. Christodoulou did write a long book about this, but he kept irrotational isentropic dynamics past the singularity, so he violates conservation of momentum and conservation of energy. Nonetheless, it's a quasi-linear wave equation, okay? And he did the development of shocks for that quasi-linear wave equation. Let's just please not call it Euler. So past this first singularity, you would like to first understand essentially two things. And maybe this is where I can switch back to the board for 2 more minutes. And what I want to define is this concept of the MGHD, which is the maximal globally hyperbolic development. So let me just very quickly talk about that. So this picture which I have here, it denotes the largest possible space-time with the following property, that if you draw any point in this space-time and you follow back the acoustic light cone, you will hit the initial data and you will not encounter any singularity. Based on this idea, you can define a maximal possible space-time with the property that the equation is hyperbolic in it and it's uniquely computable from the initial data. And this is what it should look like. Okay? This is the MGHD, maximal globally hyperbolic spacetime. Well, I'm kind of lying. Normally, when you refer to this, there's another property of the spacetime which is called inextendability. It's maximal because it's inextendable. But I just told you there's probably going to be shock collision. So because I cap everything at the board, I cannot go past the board. Okay? So this is my only caveat. It's the MGHD in a box. Okay, in a box because I need to put a time horizon. Okay, all right. Where's the shock? So step 1 of the program, of our program, is to identify this MGHD. Why you would want to do that is the following. The true shock wave, which color have I not used? Green. The true shock wave will actually be somewhere here. It's going to emerge from the pre-shock, and it's going to lie below this singular surface where the fields are C1/3. And then what you know, in addition, and I didn't draw it like that, but it's tangent. These 2 surfaces are tangent to each other at the pre-shock. So in some sense, they're indistinguishable here. So step 1 is compute acoustic dynamics up to yellow region. Step 2, use Rankine-Huguenot to compute a free surface, which is in green, and compute jumps across this free surface, which then further allow you to describe an Euler solution to the right of this Cauchy horizon and to the left of this shock surface. So it allows you to compute the Euler solution in here, including weak characteristic singularities. So the essential part of all of this is that you need to know the solution up to the Cauchy horizon because you're going to use the Cauchy horizon as a new Cauchy surface from which to emanate the Euler dynamics. And B, you need to know, if you want to compute these jumps, you need to know the traces from this side on this shock surface, wherever the shock surface may be. And because you know it's tangent to this other surface, you need to be able to essentially compute up to the yellow surface. Now, in the process, you will discover that between the shock and this yellow surface, you have initially computed something which makes no physical sense, and you indeed discard it. But a priori, you don't know that, because you don't know where the shock surface is. So in step 1, you're computing this maximal globally hyperbolic development, and in step 2, you use RH conditions to compute the physical entropy-producing weak solution. Okay? And this talk is about step 1. Yes, Jalal?
Before you do this, is it possible to have just a 2D drawing of all of these shocks, pre-shocks, and the Cauchy horizon just to see?
This is a 2D drawing.
Well, I mean, it's okay, so it's a bit, can you make
2D this is a 2D in space. Do you want 2D in space-time?
Yes.
Yes, so first singularity. No, I need to maintain the same colors. This is where the C1/3 objects will live. This is
The pre-shock.
this is the pre-shocks.
Okay.
This is the shock surface.
Okay.
And this is the Cauchy horizon is in blue, which I have forgotten.
That's okay.
Okay.
The region between the yellow and the green does not make any physical sense, you said?
No, a posteriori. After you know where the green is, a posteriori you discard it because the solution you had computed here was traced back to the data, but that's wrong. You should only trace it back to the shock curve and then use RH conditions to jump across the shock.
Oh, but okay, but you do construct the solution.
You do construct it, but not in a causal acoustic way. I mean, it is causal, just not following just acoustics. Yeah. Okay, so that's what we're trying to prove in multiple space dimensions. And if we could please go back to the slides. I will probably finish at the middle of my talk, but at least we've understood something, hopefully. Okay, so for the purpose of the talk, not for the purpose of math, it's very useful to work with isentropic dynamics, because if I'm anyway just computing the MGHD, there's no entropy produced in the MGHD. If I start isentropic, I remain isentropic, okay? So I'm just going to work with this system, in which I have, this is the remnant of the momentum equation, this is the remnant of the conservation of mass equation. Sigma is, rho to the alpha is the sound speed, rho is the density, rho to the alpha is the sound speed, square root of dp d rho. And it's convenient to not work with sound speed, but 1 over alpha times the sound speed, where alpha is just a adiabatic exponent minus 1 on 2. Okay? This is a very nice, beautiful, symmetric hyperbolic system. It has 3 wave speeds. Okay, but to describe these wave speeds, and again, for the purpose of this presentation, not for the purpose of math, let's stick to 2 space dimensions, so the dynamics is in 2 plus 1, 2 space, 1 time. Let's fix, somebody gave us from somewhere an orthonormal basis of your space domain at every time slice, an orthonormal basis that moves nicely in time. Maybe this basis is E1, E2, maybe. I don't know. Somebody gave it to you. You would like this n to somehow encode the direction of the steepening front and tau to be the direction tangent to it. Okay? Well, if you identify n and tau, then in the tangent direction, you just have the fluid velocity, you see. Nothing interesting happens. But in the normal direction, you have 3 different wave speeds corresponding to velocity plus sound speed, velocity itself, and velocity minus sound speed. And these, of course, you recognize as fast acoustics and slow acoustics. This was well known to Riemann, who, when d is equal to 1, wrote this system for the so-called Riemann variables, in which not only did he identify lambda 1 and lambda 3, but he also identified that if you do linear combinations of u and sigma, namely these linear combinations, then these become 2 coupled transport equations. Okay? So Riemann already wrote this down. And this is the picture I've been drawing before on the slide with 2 different, with different color schemes. Please focus on the picture on the left. This is 1D, 1 space, 1 time. Riemann wrote down the system, isentropic Euler. So you have 2 different wave speeds. So you have 2 different characteristics. Let's write by eta the characteristics of lambda 3 and phi the characteristics of lambda 1. The phi characteristics are in green. The eta characteristics are in yellow. And you see the eta characteristics impinge. And when they collide, that's when the pre-shock has formed. This point in space-time encodes a C1/3 cusp. The slow acoustic characteristic emanating from the pre-shock is this green curve. And that's a Cauchy horizon because if you were trying to compute the solution past it, following the fast acoustic backwards would intersect this red curve, and this red curve it's filled with singularities. You cannot cross it. The solution is not smooth across it. This is a horrible place to do analysis in, because this Eulerian frame denotes a manifold in space-time which is not smooth. It's a manifold with a boundary, and it has a kink in the boundary. It's a horrible place to do PDEs. Instead, you should take this picture and go to Lagrangian coordinates. Which Lagrangian coordinates? Because you have 3 different wave speeds. you're meant to go to the Lagrangian coordinates of the fast acoustics. Fast acoustics denote a Lagrangian frame. Write everything you can in this Lagrangian frame. So in particular, the orange lines become straight. This manifold, which is the MGHD, becomes a beautiful manifold with boundary, which is now smooth. It is much more convenient to do analysis in a smooth manifold. All our analysis is done here. At the very end, when everything is computed, we just invert eta, and we get this picture. This is what happens in 1D. In 2D, you don't have curves, you have surfaces. So you have fast acoustic surfaces and slow acoustic surfaces, denoted in red and green. When two red surfaces first touch, they impinge on each other, then it means that a singularity has formed, okay? And shock formation is identical, and it's a theorem, to fast acoustic surfaces impinging on each other. So we would like to basically take this picture and extend it up to the first singularity and beyond to the maximal globally hyperbolic spacetime. So we take an initial foliation of spacetime. We took a random choice with lines, and we pushed this foliation forward, and that's how you get these surfaces, okay? It's just a push forward of a straight line under fast acoustic and slow acoustic, okay? The MGHD in multiple space dimensions looks like that. So the Cauchy horizon, which was this curve, well, let me talk about the pre-shock first. The pre-shock is this point. In 1D, it was a point. In 2D, it's going to be a curve, and it's this black curve here. It's hard to see. Along this black curve, you have pre-shocks. These are first singularities occurring past T star, across which the fields are C1/3. Emanating from it to the left is a Cauchy horizon in green. The Euler solution does not want to be computed acoustically past this Cauchy horizon. And in red, you have a manifold of smooth, a smooth manifold along which the solution blows up everywhere. There are gradient singularities everywhere on this red manifold. Okay, the MGHD is the complement of, like, it's everything to the right and to the left of that. And we would like to not just compute these curves, but also the Euler solution in these curves. So let's say this is the goal, and you've decided to complete this goal. What are your difficulties? And the first difficulty is that I've somehow lied to you, because I started my story by saying, let's assume somebody gave you a frame, n tau. Who is this frame? The Euler equation does not come with an addendum which says use n and tau as follows, right? So everything I've told you about fast acoustics, how do you even define them? Because you don't know what n and tau are. The second issue is that, well, let's say you were smart enough to compute n and tau. Then you're going to have these characteristic surfaces. It's a very well known in geometric propagation evolution, in the geometric evolution equations, that the first fundamental form of these surfaces is very hard to get the regularity for. Second fundamental form, all good. First fundamental form, you can't. This is why when you do Ricci flow evolution, that's why the Turk trick in Ricci flow, it's exactly fixing this issue that you don't know how to compute the regularity of the first fundamental form. The third main issue is that the Riemann variables are not good anymore. They are great in 1D, they're just not good in multi-D. And then I'm just going to tell you how we overcame these difficulties and maybe even state a theorem, but I don't know. So the first issue I would like to address is what are n and tau. And it turns out that you don't really have a choice. They are there, n and tau. And let me explain how they're actually there. So at time 0, take a line. And I told you that fast acoustic surfaces are the propagation of this line forward in time under the flow velocity plus sound speed in the normal direction. But of course, you don't know what n is, right? Now take a time slice. Take a time slice of the surface, you get this curve. Now on a curve, there's a kind of a nice and unique way to define n and tau, like that, okay? So now you can ask yourself, wait. So this curve, which I've obtained from this surface, has a well-defined n, but to even define the surface, I had to know what n is. It smells like n should obey a PDE. And that's correct. You very soon discover that the only way in which this works is that if n is, of course, so this direction is x2, which is this direction. So n is, of course, the rotated two derivative. The two derivative rotated by 90 degrees. And this d phi n, eta, should solve this PDE. And this is really a conceptual new thing, because normally when we go to Lagrangian coordinates, we turn a PDE into an ODE. We go from transport equation to dt eta is u compose eta. That's the standard thing you do. That's why you go to Lagrangian coordinates, because you turn it into an ODE. This is a PDE. And it's horrible, because it's not a transport equation. If this was a two derivative, this would be a beautiful transport equation. It's a rotated two derivative. Okay? Anyway, so it turns out that if you perform this procedure, not only do you get normal and tangent vectors, but you also get a natural induced metric on the surface, which is the natural metric induced by the parametrization in Lagrangian coordinates. I put it here. So what is shock formation? So once you have identified your diffeo of fast acoustics, shock formation is that the gradient, its determinant, goes to 0. That's what it means for two surfaces to impinge on each other, is the determinant of the gradient goes to 0. So all of a sudden, you've taken something which said Eulerian quantity goes to infinity to Lagrangian quantity goes to 0. PDE analysis is better at computing zeros of smooth functions than to prove objects go to infinity in general. So you know that you have a better chance of actually proving something. What is this pre-shock? Okay. This pre-shock is the intersection of two level sets. The level set determinant of gradient eta is 0, and something having to do with the fact that along this pre-shock, it's the first time this cusp has formed. And when you say first time, you're basically saying that another derivative vanishes. And in this case, it's the normal derivative. And so you can very precisely compute this pre-shock by identifying these two codimension 1 surfaces and intersecting them to get a codimension 2 surface. And that's how you get your curve of pre-shocks. It's a graph over x2. And at each x2, there's a unique x1 and unique t star. And again, the issue I told you about is that there's what is called geometric derivative loss. Christodoulou overcomes this by very, very, very difficult analysis, which we don't do like that. There's a natural derivative loss. Basically, you cannot compute the regularity of this object. So instead, we do the following. Nothing in what I said on the previous slide would change if I reparameterize this surface tangentially. If I take this surface and I tangentially reparameterize it, nothing should conceptually change because it's the same surface. You know, the determinant of gradient eta will vanish at the same place. So what we do is what is called an ALE reparametrization. We view this surface, or at least the time slices of this surface, not as the push forward of a two-dimensional diffeomorphism of this line, but rather as a graph over this line. So instead of going from a two-dimensional diffeo, eta 1, eta 2, to a graph parametrization, you have all of a sudden reduced one dimension. Computing the second fundamental form of this and computing the first fundamental form of this is the same. Okay? So we do this tangential reparametrization, so you get a new diffeo, psi, and you get a new tangent vector, a new normal vector, a new tangent vector, and everything is encoded in this height function. And this height function obeys some kind of nonlinear PDE. And we redo all this Lagrangian description, but from the point of view of this ALE perspective. So Lagrangian shock formation is that the determinant of the gradient of the diffeo goes to 0, turns out you shouldn't work with this. You should rescale it by the induced metric, because otherwise you're going to lose the derivative. But anyway, let's not talk about this. The well-known Eulerian blow-up criterion, that the divergence of U goes to negative infinity and that the normal gradient of density goes to negative infinity, is a direct consequence of this. It's if and only if. The pre-shocks is characterized the intersection of these level sets. And in this framework that we have induced, Eulerian and normal derivatives become one derivative in ALE land, weighted by a quantity that goes to infinity. So this is very important because, you see, in Eulerian land, normal derivatives go to infinity, right? In Lagrangian or ALE land, derivatives don't go to infinity at all. It's this scalar prefactor in front of the derivative that goes to infinity. And that's very different. Because all of a sudden, I can do an analysis in which everybody is smooth, and all the blow-ups are encoded in this scalar object. OK, last difficulty are Riemann variables. If you just work with classical Riemann variables, which are written here, none of this works. And the reason is that the classical Riemann variables do not know about the geometry of these surfaces. So it turns out we came to this after a lot of trying, but a posteriori, I can always motivate how we came to this. But it turns out that you need to do the following. Instead of looking at gradients of the Riemann variables, which is what you would be tempted to do, you should take the gradients of the Riemann variables and combine them with linear combinations that encode the curvature of these fast acoustic surfaces. These 6 terms are specific curvature components of the fast acoustic surfaces. And if you do these very precise linear combinations, what you have a hope for is that these new objects, which replace the old Riemann variables, are now smooth. So our goal is to do PDE analysis, but not on the classical. So not only do we go to ALE land, we also change the fundamental variables by doing these combinations of geometry terms and PDE terms. And these are the objects on which we do analysis on. Now, of course, sorry? Psi is the diffeo, is the ALE diffeomorphism. As you can imagine, the beautiful Euler equations, not only do you have to butcher them by going to this new ALE land, you also have to butcher them because you have to write down the PDEs satisfied by this. And that's horrendous. And, OK. But the point is that there's a lot of structure in these PDEs that you know has to be there because the Euler equations had structure. Notice in particular that here, respectively here, I have 3 different transport operators. This encodes fast acoustic wave speeds, this encodes slow acoustic wave speeds, and this is encoding velocity speeds. These 3 terms, respectively, these 3 terms, when you do energy estimates, they just combine magically to cancel. And this reminds me of the hyperbolicity of the system. So they are ugly, but in fact, all the beauty that was there initially is still there up to polynomial error terms. Okay. What is the initial data? The initial data I would like to take no vacuum, and I would like to have a global minimum for a derivative. So I choose a derivative, I take D1. There's nothing special about D1. And I'm just assuming that this has a non-degenerate global minimum. And I put in red non-degenerate because the function x squared has a non-degenerate minimum. The function x to the 4 has a global minimum at the same point, but it's degenerate. Because if you perturb x squared in C infinity by a small function, it still looks like x squared just a little bit nearby, right? But if you take x to the 4 and you add epsilon times C infinity function, it doesn't look like x to the 4 anymore. It's going to look like x squared. Okay? So in that sense, that's what I mean by a non-degenerate minimum. Something which at the minimum, the Hessian is bounded from a multiple of the identity from below. Okay? And that's what the Hessian, that's actually how this field looks like near the minimum. You can clearly tell that the Hessian is bounded from below. In addition, I'm going to assume regularity. I need to work with 7 derivatives in L2. And the reason for 7 derivatives in L2 is that I really need to work with C4 functions. And the Sobolev embedding in 3 dimensions requires me to go to H7. So I wish I could do the analysis in C4 directly, sorry. What happened here? I went forward instead of backwards. Instead of working with C4, which you cannot do because this is a hyperbolic system, it begs for L2 analysis, you go to H7, okay? And now the theorem is, take initial data like this, with a global minimum, no vacuum, and 7 bounded derivatives, prove 3 theorems, essentially. Theorem number 1. These objects that I've troubled you to define remain smooth, always. And moreover, they remain smooth up to some manifold. This manifold is the paraboloid crossing through the pre-shock. So this space-time script P is a paraboloid crossing through the pre-shock, and up to this paraboloid, you can flow these fields, and they remain as smooth as the data, okay? Moreover, the diffeo is smooth as an invertible. Moreover, on the futural temporal boundary of the space-time, there's only one singularity, and it's occurring along the pre-shock. There are no singularities here nor here. So you know that here you should continue the Euler dynamics, and so should you here, continue the Euler dynamics. Theorem 2. To the right of the pre-shock, you indeed can continue the Euler dynamics up to a larger space-time, denoted by this red surface. And this red surface, you understand precisely what it is. It's the level set of this determinant of the gradient is equal to 0. And you know that everywhere along this surface, this jg is equal to 0. So every single normal derivative which carries a jg inverse goes to infinity. So there are blow-ups everywhere. Now, to the right, you have this Cauchy horizon. So you take the pre-shock, and you look at the slow acoustic passing through the pre-shock. Well, you can trace it back to the data if you want, but it could also go forward in time. And you get this surface. And the theorem says that the Euler equation can be continued uniquely and smoothly up to this level set, not level set, sorry, to this surface. You understand precisely where the surface is. And moreover, there's no blow-up along the surface. It's just dynamical inaccessibility via acoustics. This surface is indeed a weak rarefaction. That's what that surface is. Okay. Just 2 remarks to close. I had some slides about the proof, but I was advised to skip them. So 3 remarks. I've presented the talk in 2D isentropic. That's irrelevant. You can go to any dimension you want, and non-isentropic doesn't change a thing. The only thing that happens when you go to multiple space dimension, instead of 1 tangent vector, you have multiple tangent vectors. But you still have just 1 normal vector, and that's the only thing that matters. Now, whenever you have a good well-posedness theorem for a PDE, you have a good numerical scheme, should you wish to do so. So normal classical schemes for computing shocks in Euler, they use the Glimm scheme, which approximate the shock with piecewise discontinuous fields. And so they're naturally, because they use piecewise discontinuous objects, first order accurate. No matter what you do with the Glimm scheme, it's going to be first order accurate. Moreover, in multi-D, Glimm schemes are well known to be not ideal because you don't really know what is n and tau. Okay? On the other hand, I've just presented to you a theorem which said, take Euler, go to these other variables, everybody remains smooth, all derivatives of order 1, and I understand everything. So in this land, I can do a numerical scheme of arbitrary precision. If you use 4th order Runge-Kutta, like us lazy people did, then you're going to get a 4th order scheme. If you use a higher order integrator, you're going to use a higher order scheme. In this Lagrangian land. At the very end, after you've computed everything in Lagrangian land using arbitrary precision, you have to go back. Inverting, finding roots of polynomials, you can also do to arbitrary precision. It's costly, right? But you can do it to arbitrary precision. So what we have done, essentially, and Steve and a collaborator in Los Alamos already have implemented this, is an arbitrary precision numerical scheme for shock capturing, which is not first order anymore. And of course, everything here, I haven't yet done part 2 of the program. Part 2 is now to use this information about the MGHD to compute the unique multi-D shock wave, the unique rarefaction, and weak contact, prove that across these surfaces the fields are exactly C1 1/2, and everywhere else smooth. And that's in the process of writing. And I'll stop here.